on the question, cheapest flights within K-stops. It's a medium-level question, and the question states there are n cities connected by some number of flights. You're given an array of flights where flights I equals from to price. Indicates that there is a flight from to city to with cost price. You're also given three integers, source, destination, and k. Return the cheapest price from source to destination with at least aiming at most k stops. And if there is no such route, then return -1. Let's look at example 1. So the input n equals 4, there's 4 places, and then flights from 0 to 1, the cost is 100. So as you can see here, 0 to 1 it's 100, and then from 1 to 2, 100, 1 to 2 is 100, and from 2 to 0 is also 100, and then from 1 to 3 it's 600, and from 2 to 3 it's 200. And then it tells you we want to begin at source, which is 0, and then the final destination that we want to reach is 3. So basically you want to go from 0 to 3 with at most 1 stop, so k equals 1. So how can we go from 0 to 3 with at most 1 stop? There's let's look at all the ways to approach from 0 to 3. There's 0, 1, 3, which is 1 stop, stopping at 1, and then there's also 0, 1, 2, 3. This is 2 stops, so it exceeds the k equals 1, so this is an invalid path. So I got the final answer, it would be going from 0, 1, 3, which is 100 plus 600, which is 700, and the output is 700 here. The optimal path with at most 1 stop from city 0 to 3 is marked in red and has cost 100 plus 600 equals 700. Note that the path through cities 0, 1, 2, 3 is cheaper but is invalid because it uses 2 stops. So from this question, reading this, we know that we're solving for a shortest path, and this is a directed graph. So solving for shortest path in a directed graph, we can use an algorithm called the Dijkstra algorithm. And Dijkstra's algorithm basically uses BFS plus min heap. And for this algorithm, it deals with non-negative weights. So the graph all has positive weights. There can't be like a path that has like negative cost. So we're working with non-negative weights. And the idea of Dijkstra's algorithm, so we take a starting point, which is source. They give us a source which is 0, and then basically we start from source as the center and gradually expand outward while updating our shortest path to reach other vertices. And basically I can write this down. We start at source as the center and gradually expand outward while updating the shortest path to reach other vertices. And this is using like a greedy algorithm, a greedy approach. APPROACH. And then what it means is like it uses a greedy approach because for each step it selects the min weight from the priority key, because we'll be using a min heap. So it selects at each step, selects the min weight from currently reached vertices to find the shortest path to other vertices. Let's start writing our code. from collections import default dictionary, and then we're also gonna use a priority queue since this algorithm needs min heap. So I'm gonna use heap queue from heap queue, import heap push and heap pop, and we're gonna use this to build our priority queue, and we're gonna use this default dictionary of list to build our adjacency list for the graph. So first of all, let's create our adjacency list. So adjacency list equals default dictionary of list, and then now let's append data into our adjacency list. So for the flights is defined as from to price. So for source, destination, and cost and flights, let's do adjacency list source dot append cost and cost and destination. So this adjacency list will be later used for us to traverse the graph in a BFS way. And then I'm also gonna create steps because we need to keep track of how many steps we're taking. We can't exceed k steps, and for us to use Dijkstra's algorithm, we need to at each step select the min weight, and we keep updating our steps list. So I'm just gonna create the steps list here. I'm gonna create it as a dictionary, and then for Dijkstra's, we have all the steps at the beginning pointing to positive infinity. So it's gonna be something like I to float positive infinity for I in range of n, and n is how many places there are, how many nodes there are. So, and then I'm gonna initialize my priority queue. Priority queue equals, I'm gonna structure my priority queue with the cost first, and then the source, and then the steps. So the cost in the beginning will be 0, 0 from, then the source is given to us from here, and then the steps, we'll initialize the steps in the beginning as -1, because if we initialize it at 0, when we go from 0 to 1, it'll already be 1, but actually this is non-stop, right? So it should be 0. That's why we initialize it at -1. So now that we have everything set up, we can start writing our BFS. So while priority queue, we can pop our data from our priority queue. So it's gonna be cost, source, and step equals heap queue dot heap pop priority queue. And then we can have like a base check. So what is our base check? We need to check if our current node source is already at our destination. That's when we know we've reached our destination and we can return the cost. So let's do a base check. So if source equals destination, then we can return the cost here. And then we need another base check, which is if we are exceeding the k. So if step is greater than or equal to min of k or the min of steps list source, then we don't do anything. This is like a wrong edit, like this path wouldn't work because it's not within our limits or constraints. Either it exceeds k or it's greater than a previous path to that node, which then we don't need to keep track of, so we just continue. And if both of these pass, then we can keep traversing. So we'll go from, we'll start doing our BFS. So for neighbor cost, I defined the adjacency list as the cost and then the destination. So for neighbor cost and neighbor and adjacency list of source, we can do a heap queue dot heap push into our priority queue. And what we want to push is priority queue has the structure cost. So basically we add our neighbor cost to our cost here. And then our source would be the neighbor. And then step equals step plus 1. So, oh, before we do that, I missed something here. We need to update our steps list here. So steps list source equals cost. Equals step. And then after this is done, if it never returns, then we know there's no valid path. We would just return -1. And I think this is the entire Dijkstra's algorithm. Let's try running this. Oh, from collections. Steps list. Yeah, so this is our answer. Please let me know if you have any questions, and thank you so much for watching.